Welcome to the newest part of my big CNC blog project. If you don't know, I'm reconstructing my big 4-axis CNC project that I have been working for years and it never finished. So I'm gonna commit and do it now properly. And I document that as a blog series on element14.com in the motors and drivers sections. And this is basically another entry because I'm trying to get either the best one out of it, or I try to get the best bang for the buck with this machine. And of course people are asking, what kind of drivers are you using? And then I'll tell them what I already have and what I would like to have, but it's actually not that easy to decide for a specific driver or motion control system. There are a lot of factors that depend, and if you ask people, they usually just tell you, I use this one because I like it, because I've used it before, because it just fits. But where's the reasoning behind that? How do you find out which one of these hundreds of offerings is the right thing for your application? So what we are going to do today is we're gonna go to the candy shop, which is Trinamics homepage, now a part of ADI. That's why the logo is different to I'm used to. But basically they have all their products listed there with all the specs and stuff, and we'll take a look and see how do you quickly decide which of those are suitable at all, which ones could you use in your project, and then see which ones would be suitable for the machine that I'm building. So basically I'm telling you how to decide on stuff, and you should in theory now get a big picture about how you would decide that for your own project. So first I'm gonna go to the integrated sections section of the homepage, and integrated sections for Trinamic means a lot of things. We are specifically interested in the stuff that is suitable for CNC machines. So what we have here is battery powered drivers, not really, but they exist. Stepper drivers, yes, of course. Stepper gate drivers, I don't know. And then there's motion control and interface ICs. Those can be pretty interesting, but there are a lot of things to think about. So let's start with the choice that is basically not really the case for most projects that you see in the hobby sector, but it can be a great choice if you go more industrial, or if you have a very, very specific challenge that you need to solve that basically it's a simple problem, but it has to be done perfectly. So that is where you go to the motion control and interface IC stuff. Usually when you talk about like Trinamic drivers and stuff, you mean stepper drivers, the actual thing that makes the signals that makes your stepper go brr. Motion control ICs are not that thing. They also have these TMC numbers, but don't be fooled, those are not stepper drivers. So here's a really nice schematic that explains it really good. So the motor basically is what moves the axis of your CNC, of your 3D printer, of whatever machine you're building. The motor has to get its power signals from somewhere, which is the driver that is basically chopping up the power in sequences that the motor can actually use and move accordingly. And this driver has to be controlled somehow. And let's take the example of a 3D printer. Usually you have a microcontroller on there that runs a specific firmware like Gerbil, Marlin, RepRap firmware, stuff like that. And that makes the signals for the driver, and the driver moves the motor. So your motion controller is an MCU running a firmware. You could also do that by using some general microcontroller, write your custom code that beeps out these signals the driver understands and then translates it for the motor. It's one step in between that offloads workload from the controller to the driver, and that is specific for this application, so it does a much better job. But you could also go one step further by offloading all the stuff from your control MCU to a motion controller, which is a dedicated MCU that drives the driver, that drives the motor, and the motor in the best interfaces gives back information to the motion controller, so it constantly adapts in a loop, which would mean that usually these motion controllers are used in closed loop systems. So the Motion controller is actually aware of what the motor has done and not only what has been sent, and this makes this a lot more reliable. When would you use this? Let's imagine you have a factory process where you have to move this thing from here to there, and it has to be at exact the same position every time, down to the 100th of a millimeter, because some drill will come from above and drill it, and this process happens extremely fast, hundreds of times per minute, maybe even multiple times per second. If you use it the conventional way, just drive an MCU with a stepper driver, you will run into trouble with accuracy, with timing and stuff. That is where you use a motion controller. Usually when you have to interface with a system that's already running on some firmware, it has this method of controlling predetermined, you can't really move it to a motion controller in most cases, but you could. And if you're building a machine from scratch, this is a real possibility. In my case, I would decide against a motion controller under one exception. I want to use a well-maintained firmware that drives my machine, and these use a firmware I don't really intend to rewrite. They use step direction signals that goes to the motor, and the case where I would consider a motion controller is if I would use this one, the TMC 42010 and the 4361A, because those both have step direction interfaces and they can be controlled by a lot of interfaces, including step direction, which is what I use, and those would form this closed loop system. So if I would want to make it closed loop, I would have to make a thing like that. For most of your applications, you won't go into those ICs, but you should be aware that they exist, because if you try to make something that is super fast, super accurate, and does like one specific task very well, this is the way to go. And looking at integrated circuits again, let's go into the stepper drivers. Usually the first decision that you have to do is, will this work with my stuff that I already have? So we're building a CNC machine, and this applies like to most stuff. What interface does the controller use to control the driver, and that controls the motor, like in this diagram? And we basically can rule out all that only allow a specific interface. So if we go down here, we see two that do not have the step direction interface, which is the first column. These only use SPI. I don't intend to control anything with SPI, so these two have to go anyway. Okay, look at the other ones. We have a lot of stuff that works with step direction. Great, that is what I need. Next thing that I have to think about is, of course you can see, oh yeah, 2130, I know that one is used in some 3D printers. 2208, oh yeah, that's a classic for 3D printers. 2209, yes, still a classic up to 24 volt systems. But don't be fooled. Maybe those are not the right ones, and there are a lot of other options. So first thing I want to look at is, do I use any specific configuration features on my printer that would need a second interface? 2130 has SPI. That is why it was popular for a lot of 3D printers. 2208, same thing, but with UART. Also popular choice. Next thing we have to think about, how much current do we need and how much voltage do we need? The motors that I currently have on my machine run at 48 volts at 2 amps. If I look into motor supply, 46, 46, 46, 36, 36, 40, 60. We only have one choice that has step direction interface and goes up to 60 volts, so more than 48 plus a bit. And that one has only 1.4 amps. I think 1.4 amps could be enough, so I'm putting that in another tab so we can look at it later. My other option is, we have a 46 option here. 1.2 amps, not that much. We will still not go down to below 30 volts for sure. but here's a 2 amp version. But we could use one that goes up to 36 volts maybe, and try that one out if it has more current capabilities, like this one here for example. And of course we're looking at the humble 2208 because 36 volts, yes, 1.4 amps could be enough, also a solid choice. And the 2130, because that one is 46 volts, just below, we're going to 36 now. 1.2 amps could be enough. Here's a version with 1.4 amps. Let's check this one out. So these are basically candidate ICs that we could use to drive our high power axes. Let's take a look at the biggest contestant first to see if it's worth going through the hassle of converting this all. We have a chip that has stall guard 2, you can see it here, cool step and spread cycle. What are these things? It's basically, this stall guard means it can detect when it bumps into stuff, so you can detect errors or also use sensorless homing. Cool step and spread cycle are basically stuff that makes them silent and more consistent. You just need to know enough to be dangerous and then go more into depth. So we can go up to 60 volts. We got 48, so that would work. We configure them in microsteps how we want them. That's nice. And we also have all these different features. Our main problem is 1.4 amps. So what we would need to do to determine can we use this with our existing stepper motors is, can they run reliably at 1.4 amps? Currently I'm running them at 2 amps. So this one is in the choice. We would have to make a custom driver board for it, and then then basically see if it would work with the existing drivers. And that is where you usually, just to save some time, if money is not the big concern, and just get one of the evaluation boards. Drive that axis with the evaluation board. You can get graphs and stuff in the IDE. Trinamics has a quite nice IDE for that, and then you know if it's fit for the job. I personally would rather either stay with the drivers that I have on these not so, let's say these axes are not the ones that I would care the most about because they are very accurate and I have a high amount of gearing on them. So I think the 2 amps, I really want them. I want the 2 amps, but I would consider going down in voltage. So 2240 has also a lot of features. Stall guard, yes, nice, no sensors needed. Stealth of 2 is like really silent, not really needed for a CNC machine because the CNC machines are noisy by design. So, but very useful if you build machinery for home use or 3D printers or stuff like that. And they are available in different packages, and this one looks very hand solderable to me, which is nice. Oh, this preview is brand new. Yeah, we can control one axis, that's nice. 36 volts, and they also go down to 4.5, so in case we have a low voltage application, this is on the list. We have all the interface that we want, and 2.1 amps. So that is a candidate that I would really consider if I go down to 36 volts, which is dependent on what do power supplies cost. That's the next thing, because you have to factor that in. So if is it worth going down in voltage for higher holding current, or is it worth upgrading your power supply for higher voltage? It all depends on your application, and I usually am the guy that says just try it out with one of the dev kits, and so do a practical test instead of theorizing about it. In a lot of cases, it just doesn't matter at all. So basically, in a lot of CNC machines, 3D printers and stuff, it's a pretty overpowered system, so it won't make that much of a difference. it's more about precision. Let's check out the Humble 2208. A bit more limited on features, but these are the features that you really want from such a chip. I have used this in countless applications. You can see a lot of videos on Element 14 where I use this. I use it in a lot of 3D printers. Just one of the most reliable, easy to use chips I know. Goes up to 36 volts, so is an option if we go down. But let's look at the holding torque, only 1.4 amps. So now let's make the decision. We have candidates. Oh, we have another one. The 2130. This has a lot of more features. Short detection, really good one to have, but it has all the relevant features for our application. And let's check out 1.2, 1.4 amps less, but we would also have to downgrade to 36 volts. Don't overpower these chips. Don't do that. The specs are, it's a, how do you say that? Like, trinamic data sheets are very accurate. If it says 46 volts, they mean 46 volts. They don't mean 47. So I wouldn't pump 48 into that. So I would go down to the 36 volts. And so I would say, just because we would have to downgrade and less amperage, let's get rid of the 2130. That's out of the question. We have our three candidates. The one that was really powerful, up to 60 volts, but less amperage. Then we have the 2230 with a lot of amps, and it goes to 36 volt, and the 2208 that we all know and love. Let's make the decision. We have either a 36 or 48 volt system, and we want as much current as possible. At least my ideal suggestion would be 2 amps for my machine, so we could stay in the spec of the motors that we already have and wouldn't have to replace them. 2208, sorry, but no. 261C. Why do they have to make these unpronounceable names? But this one, 1.4 amps, but would be higher. Tough contestant. Or 2240, a little bit lower in voltage, but 2.1 amps. In this case, if I have to decide between those two when I buy new stepper motors anyway, I would now choose the 2240, go to 36 volts, have the higher holding torque, and all these features in case I need them. And I also think this one is cheaper than the other one, because high voltage usually means higher price. But that is only my choice if I would also get new motors. So if I find new motors that are suitable for this chip, name of 23, we need big ones, then I would use this chip or the hand solder variant if I can already get it, plus new trinamic or nanotech or something like high quality motors. But if that is too expensive, then I would stay with mine and use that setup on the one axis that I don't have drivers yet for, which is the Z axis. And I also might want to replace the motors on my B axis, the fourth axis that rolls it, because those are like pretty unreliable. I don't know much about them. They are unbranded and meh. So I would rather get those really good motors and really good drivers to have the lateral precision. And this would be my choice based on what I can see on the homepage. So you don't have to go through all the data sheets. The basic data sheets are telling you, or the basic facts are telling you enough to rule out some of the products. Let's take a look on motors. These drivers that we have looked now are used for open loop systems. So driver goes to motor, and the motor does the thing, and you usually build it in a way that you can pretty sure can you be pretty sure that the motor won't lose any steps. So you go a little bit overpowered anyway. So what we need is we need to first have the right size of motor. Pretty easy to find. NEMA flange. NEMA 17 is what you usually have on 3D printers. And we are NEMA 23 because we're having to deal with a big honking CNC machine. And now on the 23 range, we're checking out 2.8 max phase current. They all have pretty much 2.8, which also tells me, oh, and always check if the flange width and height is the right one for your NEMA specification, because if you buy some off-brand stuff, then maybe this is off by a little bit. So you sometimes get 60mm flange sold as NEMA 23, so be careful with that. Your motors might not really fit. So we can get a very powerful motor with 2.8 amps in the right size, which should also tell me that 2.8 is not that far off from the 2.1 that we saw before in current, so we should be able to drive it with that motor. And look at the product. It's also not very deep, which is good for mounting it, and don't have to stick out much. Currently my motors are like this tall, which is not preferable. I would like to have them to be a bit smaller. And we can also compare these again. They have different holding torque. Of course I want the most holding torque for my AB axis, so this would be my choice probably. Let's see, weight, height, and length is 56mm. It's like that, and has the same holding torque like such a big motor. So there's your quality, that is what you pay for. Yeah, this would be my choice of motor for the Axis. Pretty fast to find. And the driver that we had before, basically I closed that sadly, but we used the 22400++. This would be my choice of driver for the one axis that I don't have any drivers yet. One thing that I do have in stock is in the motors section. I do have a motor, one with an encoder. Looks like this, is pretty thick, so I should find it. It's a NEMA 23 and 89mm sounds about right. 2.8, I think it's that one that I have. And this is intended for my Z axis, so I already have that one. Why not use it? Big difference from this to the other motors, this one has an encoder at the back. I got this on a road test. So if you join the road test program, sometimes you get really nice parts that you can use later in your projects, like this one. And I've used this to evaluate a stepper driver. And this has an encoder output, which gives me the opportunity to try out an axis that is a closed loop, or at least get feedback so I know if I'm off. So we have this motor, we know its data. So now we have to look at just open this in a new tab. Now we're looking for a suitable driver for this one. So what do we need? What's the step gate driver? Yeah, 2160. Yeah. Okay, let's see. We basically need one of these really powerful ones. I need a step direction interface, and I think the 2160 should work because, as we can see, goes up to 60 volts, has the right interface. These are too low. Probably too low. It's the Z axis, so I want that to be really powerful to exactly position it and hold it when the bit is going into stuff. So this one looks really promising. Also, we have these two at the bottom. So let's look at all three of them. And then we have the C drivers. These are the ones with motion control systems attached to them. That gets really complicated. And then there's basically these have all the stuff inside, but I may need a motion controller in addition to that to control all the closed loop stuff. So let's first look at normal drivers, if you can directly find one that is suitable for that one. 2160, nice features. We also looked at those. We go up to 60 volt, nice. We don't have a phase current rating here. Why don't we do that? Because we can use that to control MOSFETs that we can select ourselves and then control the motor. So the amperage is not determined by this IC, it's determined by what we put after it. So if I could not find any suitable drivers, I could use this one, which also means that if I want to revise my decision that we did earlier for the B axis, I could also use a chip like that and select my own MOSFETs, basically make my own H-bridge, and then drive the big motor with how much current I want. Let's look at the next one, 2590 TA. This one also goes up to 60 volts. No mentioned rating here because same thing here, different design. So we always have to keep this reference design in mind. We can drive that one also with a lot of MOSFETs that we can select ourselves. Then we have this one here, the C262C. Haven't heard of that yet. Same thing with that one, also pretty intricate design needed to make that work, but also we're not limited. And this is the motor. So these are for me a no. Why? Because I don't want to have to deal around with this MOSFET side. I don't want to have to design that on my own. But if you have really need for really powerful motors, choose a stepper like this, design that on your own to your specs, and you have a lot more freedom. So I'm ruling those out. What I want is now look at these C drivers. C drivers have a motion controller. So here we have how they basically detect or how they determine where the motor has to go. So we can give it different data that they will follow, calculate on their own, and put the motor to use. Again, we're in the realm of super specialized one-taskers. We're not in the realm of general purpose CNC machines, so I'm not choosing those. What I could do would be use one of these motion controllers to control my axis and basically get a step direction interface from that, but basically they translate from one to the other and make a better job than I could do with an MCU. And then we have servo controller ICs. Let's look at that one. Three-phase four-wheel DC motors is not what we're going to look at today, and DC motor drivers not either. So let's check out this one. It's a servo controller. Servo means you have a motor that moves and it always gives feedback. So what I think about this one, we have closed loop control. That is its intended application. Position mode means I can tell it where stuff has to go, and it will calculate how it has to drive the motion, the stepper driver to reach that goal. Velocity mode is I can say move, like for example, constantly move, but at a set velocity, which is really good if you want to control the tool itself on a CNC machine, for example. So if you want to have the perfect speed of the tip of your spindle towards the workpiece to get the perfect cut every time, the way you would do that is have a BLDC spindle, a brushless DC motor, control that with a brushless DC motor driver, and that is controlled by a motion controller like this, and you use the velocity mode to always have the exact right speed it goes at. It doesn't need to go to a specific position, but it has to move at the perfect rate. That's how you would do that. And you can use this as well in conjunction with your normal setup to basically verify that something has reached the position. That complicates the design a lot, so you have to think about is it worth complicating the whole project that much just to have perfect velocity. For some applications, if you have a really sophisticated CNC machine, it might be worth it. If you're building a CNC lathe, I would consider that. My machine might be, in the end, I hope, be able to be used as a CNC lathe of some sort. So maybe I should give this a go on the B-axis or on the tool. And also with these you have basically, this is my interface controlled by UART or SPI. Then it goes through the skate driver, power stage, that is basically your motor driver, back via current sensing, and back with the encoder on the back of the device. So if I want to take advantage of the motor that I have, not this one, but this one, then I would need to have something like this in my loop, so it can actually read the encoder and make decision based on the encoder. Also, these encoders are basically they're similar, but they're not the same thing than a rotary encoder that you would use on when you make a knob as an input. These are much more precision, and they can deliver accurate data at much higher turning rates, or much higher RPM. And that is needed because if the data that's coming back can't be read fast enough by this IC, or isn't delivered accurately enough by the motor, then all this regulation stuff won't work properly. So if you want to do a closed loop system, you could with just a microcontroller, analog to digital input, stuff like that, but the coding has to be really tight to make that timing thing work, and usually it's much more easy to have a dedicated chip for you to do that, and usually they are also better. So I talked about evaluation kits. One thing that I use quite often, and because they are made by a German company, they have German names here. So there's one thing that is Landungsbrücke, which means landing bridge. Then there's this connection piece that's called Eselsbrücke, which means donkey bridge. And Eselsbrücke is a German word that is basically something that helps you remember something, and that is why this connecting piece has all the pinouts on here. So it basically directly helps you remember which pin does which, and you can solder directly to these pins. So you can get that out to your own hardware, connect via USB here, and read everything out, and basically control it and measure it over the TMC IDE. And this is the board where your driver is mounted. Here's the driver chip, and you can mix and match them as you want. Put them into your application. In this case, they are probably running, it looks like a BLDC motor, judging from the 3 cables that go in here. So they run a BLDC motor with that, and then determine how much its current draw, and is this chip really useful for our application, are these MOSFETs big enough, stuff like that. So if we want to have one, we basically check out the evaluation boards. Can I get one for the chip that I want to use? Of course, I've closed it again, so let's see if the stepper driver that I selected previously is available as a dev kit. This one, 2240. 2240 is available. What does that mean? Incremental, yeah. It has step direction, it has SPI, direct phase control, a temperature sensor on board, and single wide UART. So, this one is maybe it's a pretty new chip, so maybe this one isn't available yet. But I could use them, and if I would want, I'm seeing if it's already here. I have one of those. I think it was the 5160. Could be. Oh no, that's a different one. That's a different one. I have one that is compatible with the motor that has the encoder on it, so we could see how difficult it is to do. Oh, also there are these Bob boards. Bob is, if you know the step sticks that you have in 3D printers, if you take a look at a Bob board, that's basically similar to that, but it has a different form factor. But you could, if you can't get a step stick, you can get a Bob and make a little adapter board, or just hardwire it to the pinout that you want, and basically you can get it in there and get your machine back working, even if you can't get the right one yet, or if you want to try out different ones in your development hardware, then just get a Bob. You can exchange them and then decide on the right one later. I think I've got a 5160 somewhere. Yeah, that looks like it. So you have the chip, you have all the stuff around it that you need, and you can also use this as your starting point for your own design, because you have schematics and stuff here. Let's see if we can check that one out. Yeah, so this is the Bob, and we have the layout here. Do we have a schematic? Yes, we have the schematic. So basically, if I would use one of these chips that we looked before, I've also looked at these Bob chips that they have and at the evaluation boards. Usually they provide these schematics, and then basically I base my design off of these schematics. So I know this is a known working stuff that is actually recommended by the manufacturer, so it's a lot easier to get a working start with it. So just copy that basically and then go from there. Okay, as we've seen, we have some suitable options in the trinamic range. I will try to get this one working, maybe with the dev kit that I already have. I could wire that in my machine and basically abuse the dev kit as a permanent part of the machine. And judging from how complicated it is to convert my X and Y axis to closed loop, or to like a more sophisticated system, and also I would have to change the voltage it runs at, I will probably go down to 36 volts, but use the stuff that I already have, but go full ham on the B axis, the rotation, and on the Z axis, possibly even with closed loop. And I have to look into the firmware side. We are still have not decided which firmware the 3D print the CNC will run. So it could be that we use one that supports encoders and stuff. So we basically could go directly with the encoder in there so the firmware would know if it has reached a point, at least for, not for error correction directly, but at least for confirmation, so we can basically stop if something is wrong. And I would like to get rid of the homing cycle, like homing switches and stuff. I would prefer them to use the sensorless homing. yeah, probably we have to decide which axes are worth not homing with switches. Yeah, I think the B axis would prefer the B and Z would anyway profit the most from new and really good hardware. So I think we're going to have the middle ground of full fancy stuff and stuff that I already have, and then we maybe update the other stuff when there's budget and time. So yeah, thank you for joining in. This was my thought process on how to decide for chips and motors when I look at motion control systems. If you are interested in the topic and you want to know more, leave it down below. If you want to mention some errors that I made, because I'm also a human that just reads data sheets, then please put them down below and correct me. And you can follow my blog project on the Motors and Drivers section on element14.com. And let's hope that I get this thing working pretty soon. And I'm always eager for your input and ideas on how we could improve it and what we should put into that project. Have a good one.